Good afternoon to everyone. In today's class, we are going to see signals and systems. For that, we have Dr. Kishore Kumar, professor in Sri Ramakrishna College of Engineering. Uh, uh, at this point of time, I would like to invite Dr. Kishore Kumar, sir. Sir, welcome, sir.
Warm good afternoon to one and all present here. Am I
It is
audible,
being,
sir?
yes, sir, you are audible.
Yeah.
Sir, thanks
So,
for coming, sir. I think
yes, sir.
the students will be benefited by your class.
Yeah,
I'll hand over the class to you, sir.
yeah. So, I thank you once again for the coordinators and the principal and management for this opportunity to train the students, our students in the area of signals and systems for the betterment of gate improvement. That is to score very good marks in gate exams. So thus here my subject is signals and systems. So I've just combined all the departments like electrical engineering and biomedical and electronics and instrumentation and communication students. So for all these students, now we have signals and systems. I've just combined those topics, right? So these throughout this presentation, I'll be guiding you in terms of gate preparation aspects about this particular subject, signals and systems. So as a first thing, before entering into the subject in mathematical point of view of signals and systems, right, we should have some sort of some knowledge, basic knowledge on introduction about the signals and systems. So we'll start with the introduction. So whenever if we speak like signal, it is any physical phenomenon which conveys informations, right? So this is so-called signal. So without being signal, we cannot able to convert. That is, we cannot able to convey the information to the world, right? So thus, systems. That is, we, for example, to process those signals and to receive the signals, right? To produce the new signals, we need some systems. So thus, systems responds to the particular signals and thereby we can produce the new signals. So this is so-called systems. So here we need to know about the excitation or something called input signal. So here in order to actuate a particular system, any system comprises of input and output. So in order to enable the system, we need to excite the particular system by means of input signal. That is, excitation signals are applied at the system inputs. And because of this excitation input signals, right, to the systems, that particular system produces some response. That response can be treated as output signal, right? So in the diagram, it's clearly given. That is, the system comprises of input and output. So here, input signal is all termed as excitation, and output signal will be the response in lining with the excitation of the particular system, right? And here, communication system as a system example. That is, anyway, throughout this presentation, we'll be discussing about the signals today, right? So we need to know this system example. That is, in order to process the signal, we need some system. So here I have taken the example as a communication system. So this communication system has the information signals along with the addition of noises, right? Because every components or every part of the particular systems may be subjected to some sort of noise. So those noises can also be acting as a signals that will be mixed with the original signals. So this diagram comprises the communication system diagram. So which consists of transmitter, channel, receiver. If you see that the information signal, there is the signal which has to be transmitted or to be communicated, first we need to give it to the transmitter, right? So transmitter may also be subjected to some sort of noises. So this noise signal will be added with the original information signal, right, in the transmitter itself, and the transmitter output is given to the channel. The channel may be any kind, like if RF signals are used, through air we can able to transmit. And if we use some fiber optic cable, optical signals, that is the optical channels may be used. If microwave mediums are used, then your microwave components are used as a microwave signals, right? So whatever may be the channels, channel noise will also be added, right? And then we can able to transmit the signals throughout the air or something like any medium, right? Finally the receiver receives the signal, which also comprises some sort of noises. So finally you'll get the information signal which will be in noisy, right? So once if you know the basic concepts of signals, right, and systems, we need to extract the original information signal from the noisy information signal, right? So that's what I've given communication system example here. See here, these are all the various types of signals you might have been studied. Like the first and for most signal is continuous time signal, that is in analog in nature. That is, for example, the signal is given here continuous time, continuous value signal, right? And continuous time, discrete value signal. See here, this is continuous time and discrete value signals. And here continuous time, continuous value, random signals, right? So called some noises will be added. Okay, the same thing, digital signals, that is in terms of discrete time but continuous in value, right? See here, it's a continuous analog signal, and here the discrete time signal, discrete in nature but continuous in value. Okay, so that's what. So here continuous time discrete value signal, so called digital signal, right? And the same digital signal in terms of noisy, if you see in the amplitudes there may be some noises will be embedded. So this is the signal types, broad signal types. Okay, continuous time and as well as discrete time signals. So if you see that in the continuous time signals, x of t, that is inside the bracket we have to specify t, that relevance to the continuous time. Okay, whereas in the discrete time signal we need to specify the number of sequences, so called n. Okay, so x of n. So whenever x of t is specified, you should know about that particular signal will be continuous time signal. If x of n is mentioned, and that is your digital signal, so called discrete time signal. And here the conversion between the signals and the types are given. That is, first we need to go for sampling, then quantizing and encoding. Okay, that is continuous value, continuous time signals will be sampled, right, at some specified time of frequency. And we need to go for quantization, that is rounding up the nearest integer values is the process of quantization. Finally, we can have the encoding, that is we can allocate the binary digits by number of encoding methods. We can convert those continuous value, continuous time signals to the discrete value, continuous time signals through this process: sampling, quantizing and encoding. Okay, so this is the broad pictorial representation of conversions between the signal types. So how these signals can be able to, that is continuous value, continuous time signals, through this sampling, quantizing, encoding, we can convert discrete value, continuous time signals. And so in the concept of encoding, message will be encoded in form of ASCII. That is here the particular signal, that is serial binary voltage signal, for the ASCII message signal, that is here I have taken the word signal. Okay, so there is a representation of the binary voltage signal, that is drawn versus voltage in terms of time. So the signal is the ASCII message of the word signal, SIGNAL. See, this is a noisy message encoded in ASCII. There is progressively noisier signals. Okay, in terms of signal to noise ratio, various signal to noise ratio, it has been given. This noisy message, how it look like, the encoded in ASCII form, that is the representation here. Okay, and various signal to noise ratio is varied, like from 311.6159 and 51.317 and 3.20 and 12.698. For various signal to noise level, we can have the noise messages encoded in the format, ASCII format. And from that particular signals, we can recover, there is bit can be recovered in a digital signal with the concept of filtering, right? There is noiseless digital signal is given. See in the first one, noiseless digital signal and noisy digital signal and filtered signal. That is by the concept of bit detection threshold, we can able to detect the noise and we can able to get the exact signal, right? See here, the image filtering to aid the perception. That is these are all some application point of view. That is before entering into the signals and systems, why do we know we need to go for studying and what is the exact objectives of studying these types of signals and the concept of systems, right? For that purpose, no, I'm just highlighting the application point of view. There is the original X-ray image is given and filtered X-ray image is given, right? So in that we can able to extract the uh, portion of the region that we want to concentrate. And here the discrete time systems. That is in a discrete time systems, we can, that is whenever if we speak about the system, like there are two types, continuous time and discrete times. So here the example is that is the computer. There is significant events may be occurred at the end of each clock cycle. Okay, it's relevant to the particular computer user. So these discrete time systems can be defined, that is, can be described with the help of differential equations, right? So here, this equation is given now, y of n is equal to 1.97 y of n minus 1 minus y of n minus 2. So these are all low, that discrete time systems, right, excited by the signal y of n. So as I already told that n is the number of discrete time intervals, okay? So that can be elapsed since the beginning of the time. That may be n is equal to 0. And for particular example, a simply discrete time system is given. So we can able to describe any types of discrete systems with the help of equations. There is differential equations. And here, that is here 1.97 y of n minus 1 minus y of n minus 2. These n minus 1 and n minus 2, these are all a delayed signal and advanced signals. Okay, so that we'll discuss in due course. So the particular equation can be clearly expressed in terms of statements. The signal value at any time n is 1.97 times the signal value at the previous time n minus 1, the signal value at the time before that n minus 2. That is the number of occurring steps before and prior. Okay, and we can know that any signal value at any two times, we can able to compute its value with the help of discrete times. Okay, so if we increase the order, now we can able to go for the higher order systems with the help of second order differential equations and further. So here this system is given as discrete time systems. The same example is taken here. Okay, so these are all while solving the discrete time systems, I'll just teach you how this particular block diagram representation. That time now in the last module we can able to see these types of discrete time systems with the examples. The same equation is taken here, right, with the delayed elements is given here. And here the discrete time system for the particular signal is given, and the feedback systems, like there is temperature control, water level control, pouring a glass of lemonade to the top of glass, refrigerator, ice maker and driving car. Like for all these types of systems, we can be go for continuous time or discrete time systems, or sometimes both in a mixed way, like continuous time as well as discrete time, both the feedback systems. Okay, so here I think this is sound recording systems. So as I told, that signal is can be recorded by the voice message by speech. So that is by means of microphone, we can able to get the acoustic pressure variation. So microphone produces the voltage. That voltage is directly proportional to the sound. That is so-called acoustic pressure variation. And by proper electronics, we can able to get the signal, and we can convert those analog signals by means of digital. So you can get the signal in terms of numbers, binary numbers, then we can get into the computer memory for on time as well as off time analysis. Okay, so these are all recorded sound as a signal. There is SIGNAL, that is adult male voice saying the word signal. Okay, that will be the representation here. Okay, in terms of arbitrary units versus time has been taken. So every that SIGNAL, all these will be analyzed with the help of the time versus delta point at the various sequence. So with this introduction, can move to the next chapter. So here, so in this block, we'll be discussing about the mathematical descriptions of continuous time signals. Is the screen visible?
Yes, sir, it is visible.
Okay, thank you. See here, there are different types of continuous time signals have been specified here. The first one, like all these signals are continuous time signal drawn versus x of t to the time axis t. The first, if you see that amplitude modulated carrier in a communication system, and the second signal step response of an RC low pass filter, and here some like practical signal, so-called car bumper height after a car strikes speed bump. Okay, that signal may be looking like this. And light intensity from a Q switched laser, that will be like in the form of spikes. And frequency shifted key binary bit string in the form of digital means, and Manchester encoded baseband binary bit streams. So all these are all like typical continuous time signals. Okay, that is the real world signals. See, if you see that car bumper height after the car strikes, you may be getting the signals like this. And if you are using a Q switched laser, right, depending on the light intensity, you can get the signals like this. So all these signals can be related to the continuous time signals. Okay. So now you see that continuous versus continuous time signal. See, in the figure there are four graphical representations are given. So here all continuous signals that are functions of time, especially with respect to time and continuous time, but not all continuous time signals are continuous, right? So that's what in the following examples it has been given. Okay, that is g of t versus t is given for all the signals. Point of discontinuity, see here the point of discontinuity is here. Okay, so that's what we can able to convey that like all continuous signals that are specifically with respect to the functions of time or continuous time, but not all continuous time signals are continuous in nature, right? This is the concept. And see here the continuous time sinusoids, like g of t is equal to a cos of 2 pi t by t for 2 pi t by t naught plus theta. See here, this sometimes you might have been studied 2 omega t. Okay, 2 omega t. So omega is nothing but your angular frequency, that is nothing but 2 pi f. You all know that. So f is equal to 1 by t. That has been highlighted here, 2 pi t by t naught. Okay, so sometimes no, they may ask in the in the gate questions, no, they may be given in the general representation of sinusoidal forms. Okay, so that time you should know what is angular frequency and what is the time period actually, and how to calculate the frequency with the help of time period, right? So general representation, for any type of like sinusoidal voltages, or currents may be represented as A cos of omega t plus theta, right? Theta represents the phase shift. Okay, that is if you deal with the current signal and the voltage signal. Okay, so depending on the load connected, either your current signal leads the voltage, or sometimes the voltage signal lags the current. Okay, all these leading and lagging concept, no, will be depending on phase shift. So that's what. So the first A stands for your amplitude, and T naught is your time period, and theta is equal to phase shift. That may be in terms of radians. Okay. So in the cyclic frequency, in terms of cyclic frequency, I can write A cos of 2 pi f naught t plus pi. Okay, as I specified in terms of radians and in terms of frequency. Right. In terms of frequency, cyclic frequency, I can write in terms of hertz. Okay, and see here the last one, A cos of omega naught t plus pi, the radian frequency that can be measured in terms of radian per seconds. So this is the normal sinusoidal signals and the corresponding governing expression, mathematical governing expressions. Okay, either you can represent in terms of A cos 2 pi f naught t plus theta, or A cos of omega naught t plus pi. Okay, and your t naught is the total time period. And here the continuous time exponential signal. See, this is the exponential signal, right? That is e power signal, and again here A is the amplitude and your tau is the time constant. Okay, keep on goes like this. Here continuous time exponential signal, the representation, and the mathematical governing equation is g of t is equal to A e power minus t by tau. Okay, so because minus t by tau, this is your decaying exponential, right? That is from positive to negative. It's decaying response, decaying exponential signal. Therefore, it is A e power minus t by tau. And some sort of complex sinusoids, maybe that is combined from the various signals, the various adders, we can able to combine, right, to get some sort of different complex sinusoids. So that is the representation, how to combine, and in terms of real and imaginary parts, no, we can able to extract the signals. That concept is highlighted in this complex sinusoid diagram. And here these are all the representation of Signum function. So the Signum function, if you see that precise graph and as well as commonly used graph is shown here, right, to make a better understanding. Right, between -1 to 1 there is a dark line, right? So this is a commonly used graph, but the precise graph there is a dot here. Okay, and you will be getting your Signum function. That is, if t is equal to greater than 0, you will be getting 1. That is, if this is particular t direction starting from 0, if t greater than 0, that is 0, 1, 2, 3, whatever may be the value, right, you will be having 1. Similarly, if less than 0, -1. That's what the signal, this particular graphical representation can be clearly converted in terms of mathematical expression as Signum. SGN is the acronym of Signum function. SGN of t is equal to 1, that is t is greater than 0. Whereas 0 at t is equal to 0. See here, at t is equal to 0, you will get the time signal 0. And if it is -1, t less than 0. That is, for all values of minus t, you will get -1 value. Okay, so that is Signum function in a sense returns an indication of the sign of its argument. That's what we can able to understand from the graphical representation of Signum function. And unit step function. See here the unit step function, the product of g of t and u of t can be thought of as a signal g of t. Here u of t will be 1 when t greater than 0. That is, see here, this particular point t is equal to 0 and u of t will be 1 t greater than 0 for all values of t greater than 0 like 1 2 3 up to infinite, right? You will be getting 1. That's what this. And here the normal function, precise graph and the commonly used graph is given, unit step function. So the product of signal g of t and u of t can be thought of as the signal g of t. That is what I'm trying to say here, turned on at time t is equal to 0, right? That's what. So less than value, that is t less than, t is less than 0, this unit step function will be 0. So this is the mathematical governing expression. So sometimes in the questions they may indicate such sort of a graph, right? And they'll be asking the mathematical expression like in the objective types. They'll be mentioning like u of t is equal to 1 t greater than 0 and 1 by 2 t is equal to 0 and 0 t less than 0. These will be varied, right? And you need to know the exact standard form. Okay. And the example, that is the unit step function, can be mathematically described with the help of the signal, which is 0 up to some point in time and non-zero after that. Okay, here one simple RC combination of circuit is used, right, which is connected to the battery voltage VB, right, with the help of t is equal to 0. So at time t is equal to 0, the resistor may be connected to the battery, positive terminal of the battery. So here the voltage VRC of t is VBU of t and the current across the circuit and voltage across the capacitor is given here with respect to the step signal, unit step signal. Okay, that is VB by R of e power minus t by RC. That is the value of resistors and capacitor can be taken into account to calculate the time constant. Okay. And here the unit ramp function, see it is a unit ramp function. So here the ramp signal is represented as t, that is for all values of t greater than 0 it keep on increases, the linearly increased with the time. The ramp signal is linearly increased with the time. For example, if time is 1, your ramp amplitude will be 1. Time is 2, your ramp signal will be 2. Likewise, it's keep on increased in nature. Okay, and your ramp signal is 0 when t less than or equal to 0. See here, this dark line indicates this value, right? T less than or equal to 0, you will be getting the ramp signal is 0. Okay, and here we can have it as, that is t u of t. U of t will be always 1 when t greater than 0, right? That's why we are just introducing and including this u of t in all standard signals. Okay, so here the t is equal to minus 1, t is equal to 1, t is equal to 3 and t is equal to 5. Okay, that's what, where it can start, like advance, or that is your time scaling by means of proper time scaling like minus 1, 1, 3 and 5. We can able to scale the time and we can get the signals. And here the product of sine wave and ramp function. So it's the product of sine wave and ramp function, unit ramp function. We can call it as unit ramp function. This is the pictorial representation. And here we come impulse. Okay, so that is the impulse is that is your signal will be lying between minus a by 2 to plus a by 2. Okay, that is your signal impulse function can be designated as del of t. So that will become 1 by a, that is the amplitude, this 1 by a between mod of t less than a by 2. So mod of t represents either plus and minus. So inside this mod, if t is specified, it is irrespective of plus and minus direction. And this is 0, that is mod of t greater than a by 2. See here, greater than a by 2 here, the both the side, mod of a by 2 in sense like either minus a by 2 or plus a by 2, that becomes 0. When if t is greater than this particular value. Okay, in this manner we can able to govern the mathematical equation of the impulse signal. And these are all the introduction to the impulse, that is the area under the product of the two function can be represented as capital A is equal to 1 by A, that is integral minus A by 2 to A by 2 g of t dt. So here that is your impulse function, the area under the curve, the width of del of t can be approached to 0 with the standard equations like limit a tends to 0, that capital A, okay, and g of 0, limit a tends to 0, 1 by a. We are just applying the initial values, right, to get the continuous time unit impulse function. So here, finally, for the initial conditions, you can get g of 0 is equal to minus infinity to plus infinity del of t g of t dt. This is the mathematical equation for the impulse function in terms of continuous time. And here the unit step and unit impulses. See here, unit step signal is the integral of the unit impulse, and whereas this particular signal, unit impulse, is generalized derivative of the unit step. So here, see that minus a by 2 to plus a by 2. A approaches 0, your g of t approaches a unit step. Okay, and this time lag, no, that is your unit impulse. That's what g dash of t is given here. G dash of t is the approaches the unit impulse. So thus the unit step is the integral of the unit impulse, and thereby the unit impulse can be have the generalized derivative of the unit step. So there is a the relation between unit impulse and unit step. Okay, that's what I've combined the two diagram here, unit step and unit impulse. It is the integral of the unit impulse, and the unit impulse can be generalized derivative of this particular unit step. And these are all graphical representation of the impulse. Are you able to follow, the students? Can anyone, students, are you able to follow? Students, kindly respond. Any one student? Yes? Who is roll number 27? 19106 27 ECE. Are you there? You kindly respond so that I can continue. Roll number 110. ECE students. Okay, I hope you understand, and I am just continuing, right? So this is the graphical representation of the impulses. See here, the impulse is not a function in the ordinary sense, because its value at the time of its occurrence is not defined particularly. Okay, so that is del of t and del of t and del of t minus 1. That is the based on time scaling we can able to represent. And here the properties of the impulses. You see that the sampling property and scaling property is highlighted here. The sampling property extract the value of the function at any given point of time. So you can have the equation integral minus infinity to plus infinity g of t del of t minus t naught dt is equal to g of t naught. Okay, and the scaling property del of a of t minus t naught 1 divided by mod of a del of t minus t naught. So here this particular property illustrate that the impulse is different from ordinary mathematical functions. Okay, for that purpose here I am just highlighting the sampling property and scaling property is very important. And here The unit periodic impulse, that is your that can be governed by the equation del t of t. The summation of n varies from minus infinity to plus infinity and del of t minus nt. So here we can call it as n is n particular integer. So in the below there is in graph, the periodic impulse is the sum of infinitely many uniformly spaced impulses, like starting from t, 2t, right, minus t, 2t, likewise. And here the periodic impulses, okay, based on the values minus 5 and 20, minus 0.6, and between 1.2 and 50, that is with respect to del of t to the time. And here comes the standard signal unit rectangle function. So the unit rectangle function can be clearly conveyed that will be rectangle function will be 1, where t lies between less than 1 by 2. See here, mod of t. So whenever I say mod of t, it is irrespective of the signs, both plus and minus. Minus 1 by 2 to plus 1 by 2, you will be having the rectangle function value 1. Right? Similarly, that is 1 by 2, that is t is equal to 1 by 2. And it is 0, okay, if irrespective of the t value is greater than 1 by 2. Greater than 1 by 2, you can able to have 0 value. So in this manner, your unit rectangle function will be obtained. That is the product of signal g of t, rectangle of t can be thought of as the signal g of t, turned on at particular time minus 1 by 2, and similarly turned back of time at t plus 1 by 2. So within plus 1 by 2 and minus 1 by 2, you will be having the function that is so called g of t, that is your rectangle of t, unit rectangle function. And these are all the combinations of functions, okay, the various functions, signum function and unit ramp functions, sinusoid signals will be combined. That is in the first case sine 4 pi t plus 2 cos 40 pi t, and similarly the exponential signal, decaying exponential signal, can be written as e power minus 2t cos of 10 pi t, and sinc function sine of sinc of 4t, that is based on the amplitude value sine of 4 pi t by 4 pi t, and the mixed signal, right, the cos of 20 pi t plus cos of 22 pi t. These two signals will be mixed and it may be given as the representation. And here it comes shifting and scaling function. These are all very important, like you may be getting the problems on shifting and scaling of the continuous time signals. So here let a function be defined graphically like this way, that is starting from minus 1, it reaches 1 and it keep on goes linearly up to 5. Okay, so here g of t versus t. So now if t is equal to g of t, see that for minus 5 you will have 0, for minus 4 you will have 0, for minus 3 can 0, minus 2 also 0, minus 1 0, for 0 you will be having 1. That's what here, for 0 you will be having 1, and for 1 g of t value is 2. So I'm just writing. For 3 you will have 4, for 4 5, for again 5 you will have 0. So in this manner, okay, that is the graphical representation can be converted into tabular representation. So based on this, I can able to let g of t is equal to 0 with mod of t greater than 5. In this manner, I can able to define in terms of equation. And here I can go for amplitude scaling, g of t, which leads to a g of t. A is your amplitude. Similarly, I can able to shift the signals. Okay, so for the various values, the same value I mentioned now, the first graph, see here. So here for 0 1, and the same is given here, and I'm just extending the I'm just converting that amplitude. Amplitude is reduced. See here, 2.5, 1 by 2 g of t. Of the amplitude, the same time duration, but thing is, I'm just scaling the amplitude. Okay, in this manner. And here I'm just scaling minus g of t, the same value. I'm just scaling, that is, for example, a is treated as minus a. I'm just converting the positive amplitude into negative amplitudes in this particular diagram. Okay, and here time shifting can be done with the help of t minus t naught. See here in this diagram, the first diagram is the example, the second one I am just putting t minus t naught. Okay, so that is here the signal, as I told here, this is for 0 1 here. Okay, whereas in this particular 0 minus 1, right? And here for 1 0 t minus 1, and for 2 1 it is. Likewise, we can go for shifting and scaling the function with respect to the time factor. And time scaling, that is expanding and commanding signal. Compressing the signal and expanding the signals can be possibly obtained with the help of time scaling. That can be represented as t by a. The time factor a is called as expanding, that is the time expansion, and time compression. Based on the time factor value, we can do these two types of operation under time scaling. And here we can have the multiple transformations g of t, which tends to a g of t minus t naught by a, and multiple transformations can be done in the various steps like amplitude scaling and time scaling, right, with respect to t minus t naught, and compressing t by a, right, and expansion. For this, all these factors will be employed in shifting and scaling functions. See here, simultaneous scaling and shifting. That is, in the first one, amplitude scaling, that is g of t is converted in terms of minus 2 g of t. Okay, and here the time scaling, that is time expanding. Okay, so here between these values I am just expanding by means of time scaling the factor a. I am expanding, and now time shifting. Okay, so starting from 2 is shifted here, and this value starts from particular 0, and thereby we can able to perform shifting and scaling, right? Simultaneous scaling and shifting can also be possible as per the sequence, right? See here, the first signal is the given signal. That signal can be converted into time scaling, right? That is amplitude is amplitude. After following amplitude scaling, time scaling is done. There is expansion, time expansion is done, and thereby the shifting of time, that is starting from minus 4. Previously it was minus 2. That is, we are just advancing the signal, delaying and advancing. There are two possible cases of time shifting. Either you can able to delay the signal, or you can able to advance the signal. Okay, so here I have just made it advance the signal by the factor of 4. And next example, same, the combination of simultaneous scaling and shifting is done for this particular signal, so-called ramp signal. Okay, so it has been amplitude is value is 1 between minus 1 to 1. So amplitude scaling is done as 3 times g of t. Simply multiply the value in terms of 3, right? You will get 3 g of t, right, within the same time limit, minus 1 to plus 1. And time shifting, I'm just delaying the signal, right? See, it starts from, see here, for example, this is 0 1 minus 1 minus 2, right? I'm just starting from minus 1. So therefore time shifting is carried out here. And time scaling, there is time scaling. I'm just reversing the positive values of t into negative value and as well as compression. The two simultaneous function is obtained here under the time scaling. So this g of t through this amplitude scaling and time shifting, and after this time scaling, this become 3g of minus 2t minus 1. Okay, so like this signals questions may be periodically asked in your objective type questions like competitive exams, and even in the gate, no, you can get the questions like this. And likewise these are all rectangle pulses, and you just make the note and do this, right? Just to make a note if you want to make a screenshot, and you can have a practice of questions. And shifting and scaling functions, so as discussed, there is your original signal, amplitude scaled, time scaled, and time shifted for the different examples I am showing here. Okay. So here G2 of t signal, AG1 of Wt minus T naught, this time delay, that we need to find out the time factor from this graph. Okay. The original signals, amplitude scaling function, time shifted function, and time scaled function with the specified durations of the time. So likewise, no, we can able to get the information from the shifting and scaling aspects to determine the exact time scaling and as well as time compression. So now the differentiation. See here, the signals can be differentiated. X of t can be differentiated. You will get dx of t in this manner. Okay. If the signal function is x of t is like this, if it is differentiated, you will get in this manner. Okay, and if the triangular waveform is differentiated, you will get the square waveform like this. Okay, differentiation concept. And integration, you all know that sine can be converted as cos, cos can be converted as minus sine, likewise. Okay. So here even and odd signals. How to represent even and odd signals? That is g of t is equal to g of minus t. It should be satisfied. Then we can able to say it is even function. Odd function, g of t is equal to minus g of minus t. Okay. Then those signals can be treated as odd functions, odd signals, even and odd signals. See here, there is a formula to calculate the even part of the function and odd part of the function. Okay, that is g suffix key represents the even part, that is g of t plus g of minus t by 2. You have to take g of t value and make it time reversal g of minus t, and you have to add and make it divided by 2. You will get even part. Odd part, the same thing, g of t minus g of minus t divided by 2. So here the function whose even part is 0 is particularly odd, and a function whose odd part is 0 which is even. Okay. So here the derivative of an even function is odd and the derivative of an odd function is even. This confirmation can be taken from the previous statement. So thus the integral of an even function is an odd function plus the constant. Particularly the integral of an odd function is even. So these observations can be made from the even and odd parts of the functions. Okay. So these are all the representations like even and odd parts, how to extract. This is the signal. Consider G of t is the signal is given here. Even part is extracted here. This is your even part. See this one and this one, okay, and this one. And similarly for odd part, this one, okay. How can we do this? That is by means of this formula. We have to add these two signal and make it by 2. You'll get even part, and you have to subtract this two signal, that is the original signal, time reversal signal, to make the difference and make it divided by 2. You will get odd part. Okay, in this manner you can able to get the even and odd parts of the particular signal. And products of even and odd functions. See here, we are just multiplying g1 of t and g2 of t. g1 of t is a simple sinusoidal curve, and g2 of t is similarly like triangular waveframe. I'm just combining, that is multiplying the signal. So you will get the signal like this, g1 of t, g2 of t. Okay, in this manner we can able to go for product of getting even and odd functions. And here an even function and odd function for this another signal g1 of t and g2 of t, that is sinusoidal signal is multiplied with the square signal. So you will get g1 of t, g2 of t in this form. Okay, and similarly here two time varying signals, so called g1 of t and g2 of t is multiplied. Finally you will get g1 of t, g2 of t in this form, right? So these are all with relevant to the even function and odd function property. So here one ramp signal is just multiplied with the sinusoidal signal. You will get the signal g1 of t and g2 of t as specified. And see here the integral of even and odd functions. Okay, so we need to go for area under the curve. That is area number 1 is equal to area number 2 is specified here. Okay, similarly for odd function, area number 1 is equal to minus area number 2. So in both the cases we can able to go for writing the integral value between minus a2 plus a g of t dt, which is equal to 2 integral 0 to a g of t dt. Okay, the thing is it starts from minus a to a and here 0 to a, and in the odd function minus a to a g of t dt is equal to 0. So this is the function to represent even and as well as odd functions. And with this this is the example. We have to evaluate the integral. That is this is one of the important question. Integral minus 10 to 10 4 rectangle of t by 8 into e power j2 pi t by 16 dt. So you need to evaluate and we have to get the value. So your rectangle function can be written as in terms of real and imaginary part, that is even and odd signals. The imaginary parts you'll be having your odd signals, odd parts, cos of pi t by 8 plus j sine of pi t by 8. Okay, so we can convert the integration between 0 to 4 cos pi t by 8 dt plus j8 integral minus 4 to plus 4 sine of pi t by 8. Okay, so obviously the second term will become 0 because sine of pi it will become 0. So you'll get you can integrate the value cos of pi t by 8, you'll get sine of pi t by 8 by 8 and apply the limit 0 to 4. So upper limit minus lower limit, if you put 64 by pi, 1 minus 0 will be there. So the 64 pi will be the answer, approximately 20.372. This is the answer for this particular questions. Okay, so thus you need to know about the trigonometric identities here, right? So while doing the preparation of these types of signals and systems, you should know the trigonometric identities and Euler's theorems, right? How to represent the in terms of cos signals, how to convert cosine waveforms into sine, right? Sometimes we need to have use both either sine waveform or cosine waveform. In those cases, so you need to know about the basic formula, how to convert the sine signal to cosine signal and cosine signal to sine signals. Okay. This is a periodic signals. Next, periodic signal. So whenever if I say periodic signal, for it, you know that the particular signal, you know the time period, and every time period, no, it has to repeat the cycle. Okay, that is, if a function g of t is a periodic, suppose if I am saying it is a periodic, then g of t plus nt, that is where n is any integer and t is the period of the function. Okay, whatever may be the value of n, okay, that should be added with the time period. So now the minimum positive value of t, particularly for g of t is equal to g of t plus t. But in this case, your t naught is the fundamental period of the particular function, right? So if the condition is satisfied, I can say the signal is periodic in nature, right? For example, nt, that is your g of t is added with nt, your n is any integer and t is the period of function. So at every cycle repeats, the same signal will be keep on repeating, right, without any time lapse. So such a signal can be termed as periodic signal. Okay. So obviously if the statement is not followed, then we can say the periodic signal is non-periodic, but in more technically we can speak about aperiodic. Right? A function that is not periodic is said to be aperiodic. Right? We cannot say it's a non-periodic signal. More technically we can say it is a aperiodic signal. And sums of periodic functions. So here, first sinusoid, second sinusoid, two periods of the sum can be represented as in this diagram. That is the period of the sum of the periodic functions, which is the least common multiple of the periods of the individual functions. Right? If you see that diagram, first and second sinusoids, two periods of sums can be taken into consideration. The sum function is aperiodic finally, right? If the least common multiple is infinite, then the final signal may be aperiodic. That's to represent, I've just given the two examples, first sinusoid and second sinusoid, and after becoming the sum of the two periods of the sinusoids, no, that may leads to aperiodic. That representation is highlighted here. And these are all some analog to digital converter waveforms, asymmetric waveform and pulse width, and resulting pulse waveform, and symmetric waveform along with the pulse width, and resulting pulse waveform can be given, right? So these can be described by the exact periodic repetition by a particular ramp written to the zero by a negative step or by a periodic repetition of a triangle shaped function. Okay. This can be obtained from the normal analog to digital converters. And signal energy and power. So this is one of the important topic in the signals. The energy of the signal x of t can be governed by the mathematical equation as Ex equal to integral minus infinity to plus infinity, that is x of t to the power mod of square dt. This is the energy signal formula. So here the signal energy and power can be given here. Area is equal to signal energy in this manner. That is the your amplitude can be represented as A and B, right? So between this power and the signal energy can be calculated with the help of area. Okay. And these are the example for signal energy and power for the rectangular functions. Okay, that example is given here. We need to find the signal energy of x of t. So this is one of very important question in your gate preparation. So we need to find the signal energy. X of t is equal to 2 rectangle of t by 2 minus 4 rectangle of t plus 1 by 4 du of t plus 2. Okay, this is the example. Kindly make a note. And some signals have infinite signal energy. Inlining to that particular signal, it is more convenient to deal with the average signal power. So thus the average signal power can be given as P suffix x. That is your average signal power. Limit t tends to infinity. The formula 1 by t, the integral minus t by 2 to t by 2 mod of x of t square et. So this is the formula to calculate the average signal power. Similarly, for a periodic signal, the average signal power is given. That is, since it's a periodic signal, I can just write 1 by t integral t x of t t square t. That is, your t is any period of the signal. For periodic signal, I can write my average signal power formula like this. So thus signal energy and power, we can have a signal with finite signal energy is called an energy signal, and a signal with infinite signal energy and a finite average signal power is called a power signal. So this is the difference between your energy and power signal. Okay, so energy signal is a signal with finite signal energy. That's what. But whereas power signal, signal with infinite signal energy and finite average signal power is specifically called as power signal. Okay, and this is another example to calculate the average signal power for the fundamental period 12 for the ramp function. Okay, you can have the formula and we can able to simply substitute the exact value inside the integral value, then you can make it. The ramp signal is so called t by 5. Okay, you can just make integral and apply the limits, you can get the values. So here the two modules completed, that is your basic signal representations and the standard signal representations. Okay, so any doubts here, you can kindly interact. So far we have completed two modules. If you have any doubts, just go through. I'm just recalling. Just go through the slides. If you want to have any questions, you just interact. So this these are all the revisions in this module. Any doubts? Can we go for another module? So we have just seen these shifting and scaling functions. Okay, how to convert the transformations, the various steps by means of amplitude scaling. We have just discussed. Okay, for the given example, simultaneous scaling, amplitude scaling and time scaling, time shifting is incorporated. That was given for the various examples. And differentiation integration concept was introduced, and how to become familiarized with even and odd signals was specified, and how to extract even part and odd part of the signal with the help of formula is highlighted, and along with the graphical representation it was taught, and how to make product of even and odd function was discussed. Okay, with several examples, and periodic signals have been discussed with fundamental period, and how to conclude aperiodic signals, and how to combine the periodic functions was discussed, and energy and power formula, and how to determine the energy and powers can be obtained from the given problems was discussed. Okay, so now we can go to the third module. So continuous time signal was over. Now we can go to the discrete time signal descriptions. Okay. Mohan sir, am I audible sir? Those who are in the meeting, kindly respond. Am I audible? Is my screen visible? Okay. Okay. I understand that the screen is visible and my voice is audible. So I am proceeding, right? So discrete time signal descriptions. So here the sampling and discrete time. So as specified in the previous module, sampling is the acquisition of the values of a continuous time signal at discrete points in time. So in the previous module, I was particularly speaking about x of t, which is a continuous time signal. Whereas this module is a continuous time, that is your signal in terms of digital means, that is x of n, which is a discrete time signal. See in the diagram, it is given sampling and uniform sampling. Okay, so x of t is a continuous time signal and x of n is a discrete time signal. Okay, so x of n is equal to x of nts, where ts is the time between the samples. So here I can represent sampling and as well as uniform sampling for x of t to x of n. So depending on the switch, opening and closing, the x of t will be sampled at discrete steps, right? The discrete steps will be determined by the sampling frequency of the switch. That's what we can able to conclude from this diagram. Okay. See here the sampling and discrete time. Some continuous time signal is sampled, right? And the corresponding continuous time signal, sampled signal is given in the discrete steps. Okay. And here the sinusoids. The general form of periodic sinusoid with fundamental period n naught is nothing but g of n. As specified now, the standard form of sinusoid can be represented as either a cos of 2 pi f naught n plus theta or a cos of pi omega n naught n plus pi. Whereas in the previous notations, I was used that omega for continuous time signal, and here this notation is used to differentiate continuous time and discrete time signals. Okay, so unlike a continuous time sinusoid, a discrete time sinusoid is not necessarily periodic. Okay, this is a particular true statement. So if a sinusoid has the form of g of n is equal to a cos of 2 pi f naught n plus theta, then here capital F naught, no, it must be a ratio of integers. Maybe call it as a rational number, right, for g of n to be a periodic. So this f naught is an rational in the form of q by n. Okay, so that is your for all common factors in q and n naught, that is the specific period. Okay, these are all the various representations of sinusoids. See here, x of n is given as sin 2 pi f naught n for f naught is equal to 1 by 16. Whereas in the B, the diagram B, if it is 2 by 16, okay, periodic in nature. Similarly, third diagram C, there is your fundamental period 11 by 16, which is also being periodic. See here, every time it will come in repeats. Whereas this signal pi by 16, it is aperiodic. That is non-periodic in nature. Okay. And here it is an aperiodic sinusoid can be represented in this manner. Okay. X of n versus n for plus or minus 64 samples. It is an aperiodic sinusoidal representation. So now the two sinusoids with the help of analytical expressions maybe looks different, like a cos of 2 pi f naught 1 n plus theta and g2 of n is equal to a cos of 2 pi f naught 2 n plus theta may actually be the same. So here for representation f naught 2 can be written as f naught 1 plus m. This small m, no, see here this small m is an integer because that n number of discrete time, no, it's therefore it is called as integer. Okay, so this particular equations can be clearly visible in the graphical representation, g1 of n and g2 of n. That is your 2 pi n by 5 and 12 pi n by 5. In this manner we can able to represent the sinusoids. Okay, so x of n is equal to cos of 2 pi fn. So its dashed line is x of t, so which is nothing but cos 2 pi ft. The simple representation is for the various values of f. I have just highlighted here. F is equal to 0, f is equal to 0 0.25, 0.5, 0.75, likewise, right? For all the figures I have just given in the value. The dashed line, it has been represented as x of t. Continuous time signal embed with the discrete time signal. Okay, the dashed line is continuous time signal x of t. Okay, to make the better clarity, I've just combined here the both x of n and your x of t. I hope you understand. And now the exponential. Okay, the form of the exponential is x of n is equal to a alpha to the power n, or sometimes we can call it as exponential a e power beta n. Okay, so it is real time signal and complex time signals is given specified for the various values, real time and complex signals. And similarly the unit impulse functions. The discrete time unit impulse is also known as the delta function, is sometimes Kronecker delta function can be called it as. It is the function in the ordinary sense, that is with the continuous time unit impulse. It has a sampling property, and we can have the governing equation summation of n is equal to minus infinity to plus infinity, right? So here we are dealing with digital signals, right? Summation is the ultimate form, whereas in the continuous time signal the integration will be used. So a del of n minus n naught x of n is equal to a x of n naught. Okay, so for any value of del of n I can write del of a n for any non-zero, and this small a is called it as finite integer a. And here the unit sequence function. Okay, that is u of n will be 1 when n greater than or equal to 0. The same as specified in the previous module, I have just given u of n is equal to 1 between n greater than or equal to 0. Similarly, it is 0 for n less than 0. It's clearly depicted. And signum function, signum of n is equal to 1 where n greater than 0, all these values. And it is 0 when n particularly 0. And if it is minus 1 for all values of n less than 0, I mean to say for all minus values of n, right? And unit ramp function. So this is the ramp of n is equal to n where n is greater than or equal to 0. So which is specified in the ramp signal along with the amplitudes. So thus your 0 value in pertinent to n less than 0. Okay, so I can write summation of m varies from minus infinity to up to n is u of m minus 1 is the ramp function governing equation. The periodic impulse function del of n is equal to summation of m tends to minus into plus infinity and del of n minus mn. Okay, this is the periodic impulse function graphical representation. And for scaling and shifting function as specified in the same continuous time signal, here we need to go for discrete type events. Okay, let g of n be graphically defined by this particular diagram. See here for n value and g of n is given. N value for minus 1 it is 1. Okay, for 0 it is 2, and for 1 it is 3, and for 2 it is 4, likewise 3, 4, 5, 6, 7, right, is given, right? So see here all these values, the corresponding amplitude is given. Okay, so this value can be written as g of n is equal to 0 mod of n less than 15. Okay, for less than 15 it is nothing but 0 value. Likewise I can able to write the equation for the given waveform. Okay, so they may be asking by giving the pictorial representation of such sort of function, and they'll be having the multiple options for the equations. And time shifting concept, that is your n plus n naught, that is we need to shift either shifting maybe comprises of two aspects like a delay and as well as advance. Okay, n plus n naught. Depending on the time factor value, right? Minus and plus, you need to delay or you need to advance the signal. The example is given here for n plus 3 value. Okay, n plus 3. See here, this is the original signal g of n starting from minus 1. See here, this is 0, this is minus 1. Okay, this is n plus 3. So we need to advance the signal. See here, minus 1, minus 2, minus 3, minus 4. That is, time factor is 3, n plus 3. That is, it advances the signal. Okay, originally it was from minus 1. Now, after g of n plus 3, it starts from minus 4. Okay, that's what here. Originally it was from minus 1. After g of n plus 3, it starts from minus 4. Okay, and scaling and shifting function for time compression. We are just compression as specified in the module 2, right? For continuous time signal, I was discussing about the compression and expansion signal. So here, the discrete time signal compression is carried out here. Okay, where n tends to kn, the kn is nothing but the integer value. In this manner, you can able to compress 2 times. The compression factor is 2. Okay, and time expansion, you have to go for n tends to n by k, where k greater than 1. So for all such n by k is an integer. Therefore, g of n by k is defined. That is, we can able to expand the signal. But for all n such that n by k is not an integer, right? So g of n by k is not defined. Okay. See here, there is a form of time expansion that is very useful. See, let y of n is equal to x of n by m. Here the n by m is an integer and y of n is equal to 0 otherwise for all values of n. Okay. So all values of y are defined here, and this type of time expansion is actually used in some digital signal processing operations. And here the differencing, backward differences and forward differences is given here for x of n and for x of n minus x of n minus 1. Okay, and for x of n plus 1 minus x of n and x of n plus 1 minus x of n. For all these values, you can able to go for backward and as well as forward differences. And here the accumulation comes, summation of m varies from minus into up to n h of m. Okay, so this is the representation of for the various signals h of n, g of n, how to accumulate your h of n, g of n in the equations. So here also we need to find out even and odd signals in the digital signals. Discrete time events, g of n is equal to g of minus n, whereas in the previous module x of t is equal to x of minus t is specified and x of t is equal to minus x of t, x of minus t was specified for odd function. The same thing, but with respect to number of sequences you need to follow. Right, even function g of n is represented here, g of n plus g of minus n by 2. Odd function can be obtained, g of n minus g of minus n by 2. So in this manner you can able to use this formula to extract even and odd signals, especially for discrete time signals, right? So products of even and odd functions, two even functions can be multiplied, and once g1 of n and g2 of n is multiplied, you will get the function g1 of n into g2 of n as in the case. So you need to follow even and odd functions properties. Okay, and products of even and odd functions, the same, another example is given here. Two odd functions can be multiplied, and symmetric finite summation, even function and odd functions may be used here. and periodic functions. Now periodic functions for even a periodic function is one that is invariant to the change of variable, that is your n leads to n plus mn, where the capital M is the period of the function and m is any form of integer. Okay, now the minimum positive integer value can be treated as capital N. For that particular value, g of n can be g of small n plus n. Okay, so here the capital N naught may be call it as fundamental period. And these are all some of the periodic functions. You need to find out the fundamental periods. Okay. For the various examples given. So you need to go for taking LCM 3624. Therefore 72 is the fundamental period in these above examples. Okay. And for second examples, we need to determine the fundamental periods of cos of 5 pi n by 13 plus sine of 8 pi n by 39. Okay, the second value cos of 2 pi n by of 5 by 2 6 plus sine of 2 pi n by 4 by 39. So you need to go for taking 26 and 39 as n naught and n naught in the two subsequent signals. So you will get 78 as fundamental period. Okay. Signal energy and power. The signal energy of the signal x of n is Ex is equal to summation of n varies from minus infinity to plus infinity x of n square. Okay. Whereas in the previous case integral and x of t. So here the summation and x of n. So here the signal energy and power. For x of n is given x of n square and summation of x of n square. Signal energy is obtained here. And one example is given here. Find the signal energy for this particular problem. That is x of n is equal to 5 by 3 of 2 power n. That n value lies between 0 to 8. Otherwise x of n is 0. For this you write the formula. Summation of n varies from minus infinity to plus infinity x of n square. Simply substitute this value 5 by 3 2 power n, this square 2 square, right? So now you just insert this value. So you will become, there is 0 to summation of 0 to 7, and we can have 5 by 3 to the power 4 to the power n. So this is this formula, this is the standard formula I am writing. There is summation of n varies from 0 to n, a power n. That formula I am using, that standard identity is using. With that identity I can write summation of n varies from 0 to 7, 5 by 3 for 4 to the power n. Okay. And here the signal energy and power. That is, for some signals have infinite signal energy. So in that particular case we have to use more convenient to deal with the average signal power. So the average signal power of the discrete time signal is given as Px limit n varies from infinity, that is 1 by 2n, again summation of n varies from minus n to n minus 1. Okay. And for periodic signal we can write the notation summation of n is equal to that notation, the expansion, it is estimate. Okay, this symbol is estimate, and which means the sum over any set of consecutive ends in the particular sequence of length. And signal energy and power is available. So a signal with the finite signal energy is called an energy signal, and a signal with infinite signal energy and finite average signal power is called a power signal, right? So we have completed 3 modules. I'm just revising the 3rd module. Okay. just go through the presentation. If you have any doubts, you just ask me. See, three modules have been completed. Okay, introduction and continuous time signals and discrete time signals. Right. So with this, I've given some quiz to the students. In the chat box, I've given a quiz link. You kindly enter your mail ID and you can just answer the questions. So with these three modules, we close the session today. The remaining sessions will be discussed tomorrow. Okay? Thank you.